Okay, let's get started. Um, okay, let's get started. Okay, hi everyone. Welcome to the exercise class 4. I'm Raymond. So I will be responsible for this exercise class. First of all, I'd like to apologize for the very delayed posting of the exercise class. I hope that didn't bring any inconvenience to you. And I truly hope that you guys have had a very happy Chinese New Year holidays. Although I know that many of you are working very hard on problem set 3 before, and maybe even problem set 4 currently. Okay, well, anyway, so without any further ado, let's get started. So this exercise class 4 actually consists of 2 parts. Okay, the first part is about addition of velocities, and the second part is about transformation of 4 velocities. Okay, so actually both of these concepts is heavily depending on Lorentz transformation. Okay, so Lorentz transformation is the main role here, because obviously problem set 4 is mainly about special relativity, and special relativity is nothing but Lorentz transformation. Okay, so today we would like to take a deeper look at this. So for the first part here, addition of velocities, the motivation of doing this is because there is a question in problem set 4 that asks you to derive the law of addition of velocities. Okay, but the question asks you to use the concept of 4 velocities to derive this addition law. Okay, so but actually there's another way to do that, which is what I want to show you here today. Namely, instead of using the 4 velocities, we can just use the coordinates of points in space-time, okay, to do the derivation. Okay, so the question setting is as follows. So we now have 3 observers, okay, A, B, and C. Okay, A is stationary, okay, or the so-called inertial frame, and then B move in the positive x direction of A, and A perceives the speed of B as v. Okay, so up to here, everything is still very standard, right? So one frame is moving with respect to another frame in the speed of v, and the direction is actually just limited to positive x direction. Okay, so no y direction and no z direction. And actually, that's also the same for C. Okay, so C is said to be moving in the positive x direction as well, of both A and B. But of course, the speed that A and B perceive that C is moving are different, right? So A perceive the speed as W and B perceive as U. Okay, so maybe it's a good idea for you to pause a bit and then try to draw the picture of who is moving with what speed with respect to which observer. Okay. Okay, so after you have the clear picture of a scenario, so let's get to the questions. So the question is very straightforward. So what is the relationship between these 3 quantities, right? V, U, and W, okay, the 3 speeds that in the scenario. Okay, and of course we are assuming that speeds are constant here. Okay, it's a very standard setting in special relativity. Before we have relativity, the Galilean logic suggests that the relationship is just simply W equals to U plus V, right? But if you are really familiar with relativity, you should be able to tell very quickly what this equation here is wrong. What was wrong about this equation, right? Actually, we'll get to this very soon, but maybe here you can quickly ask yourself why this doesn't make sense in relativity. Okay, okay, so again, as I mentioned, Lorentz transformation is the key. Okay, it's a key role in all the calculations in special relativity. So let's see how we can do this. So first of all, we define the the space-time point, okay, the coordinates of the space-time points at each of the observers. So A, we have the unprimed quantity, okay, and B is the primed quantity here, and C has a double primed quantity. Okay, so all these things here are just the coordinates of points of the space-time as measured by A, B, and C respectively. Okay. And as we have mentioned that they are moving in different speeds relative to one another, V, U, and W. And if you're very familiar with special relativity, it's a very customary for us to define a quantity called beta, which is usually defined as V over the speed of light c, something like this. And then there would be a corresponding value of gamma here, which is defined like this, right? And of course, it is about V here, okay, just about V. But because different observer have different measurements of different observers' speeds, we have U and W. So we should also have different value of beta, okay, for this kind of different speeds. So to avoid confusion here, we use alpha and delta to denote these quantities. And then for the gamma-like term, we use the primed and double primed to denote these kind of things here, which includes alpha and delta, okay, respectively. Okay, so you see here is alpha, here is delta. Okay, so these are the definition, these are the settings that we have for this question. So now let's consider the Lorentz transformation between A and B. Okay, I said between A and B, but actually we have to specify whether the transformation is from A to B or from B to A. Okay, I hope that you can get the difference. So now we are actually looking at the Lorentz transformation from A to B. Okay, which means that this is the Lorentz transformation, and the vector that the Lorentz transformation matrix acts on should be the one that A has, right? So the vector, the column vector here belongs to A, and then after we imposing this Lorentz transformation matrix, we will get something else, which is the coordinates of space-time point of B. Okay, so this is the very familiar Lorentz transformation from frame A to frame B. Okay, and then similarly, we can also write out the same Lorentz transformation from B to C, right? So from B to C, it should be something like this, right? So we call that a primed quantity is B's quantities, and C's quantities is double primed. So obviously, this is the Lorentz transformation from frame B to frame C. Okay, and of course, we have to be very careful that we can no longer use gamma and beta here in this transformation because we are talking about B and C, right? So we call that the speeds of C perceived by B is U, and U belongs to the second line here. So the correct quantities to use is alpha and gamma primed. Okay, so this is the alpha and gamma primed quantity here. Okay, so this is the transformation from B to C. But we can also plug in the results here. Okay, the results here, which is the primed quantities here on the left hand side to this vector here, right? So we can just directly plug in the whole chunks of things here into this vector, okay, which is the second line here. Okay, I hope at this point you're convinced that this second line is true. And then after some little algebra, we should be able to get to this line, right? So we have this big chunk of transformation matrix act on act on the quantities of A, okay, and we still get the quantities of C here. So actually, the last line here represents the Lorentz transformation from A to C here. Okay. Okay, I hope that at this point you're convinced that this is true. And now I think you might have noticed that actually there's another way to write the Lorentz transformation from frame A to frame C, right? Because as we mentioned, from the perspective of A, the speed of C is W, right? And for W, we have this kind of quantities here, right? Delta here, and also gamma double prime here. So in other words, we can also write down the Lorentz transformation from A to C this way, right? So the form looks exactly the same. We just change the contents of the matrix and also the left-hand side here and the right-hand side here. So we have the double prime gamma here and delta here. So this is Lorentz transformation from frame A to frame C. So because both of these are also representing the same Lorentz transformation from frame A to frame C, this matrix here should be the same as the matrix here, okay? And that's why we should be able to get these two equations here, okay? So you might want to spend a little time to verify the results here, okay? And if you are observant enough, you should be able to see that the quantity here, okay, the diagonal quantity here, the double prime gamma here and the prime gamma here is the same. And also the same for the matrix here, okay? This quantity is the same as this quantity, okay? And also this quantity here is the same as this quantity, okay? The same here, right? So that's why we have two equations and we just simply relate the two equations, the two matrices here to get these two equations. And then, because now we actually interested in the addition laws of the velocities, so that's why we want to rewrite the gamma-like terms here, like the gamma, prime gamma, and double prime gamma, and also the alpha, beta, and delta in terms of the velocity itself, right? Namely beta, alpha, and delta here. So we now have these terms here, okay? We are replacing the gamma-like term by using the alpha, delta, and beta to get to these lines according to the definition. And then a little bit more algebra will show that from these two equations, we will get these results, okay? And then we further make use of the definition of delta, alpha, and beta, which is nothing but the velocities over the speed of light. It should be very straightforward to show that these results will lead to the final results here. So this is the correct relativistic version of the addition law of velocities. Okay, so at this point, I'd like to make some comments about this expression. So there are two extreme conditions to consider to make you understand more about this formula. The first condition is that when u and v are both very small, okay, compared to the speed of light, okay, then this fraction here would be very small, right? Because u is very small, v is very small, and the c squared is very big. So this fraction here is very small, which means that the whole equation here is approximately the Galilean version of additional law, W equals to U plus V. Okay, so this actually means that in the so-called Newtonian limit, where the speed is not too high as compared to the speed of light, this equation actually approximately holds, right? Which actually matches quite matches our daily experience, right? But on the other hand, by writing the formula like this, we can also limit the W here so that it won't exceed the speed of light. To see that, we can just plug in U equal to C and V equal to C, okay? So assuming that both B and C are moving at the speed of light, okay? So we will see that after plugging in U equal to C and V equal to C into this formula, W actually is also equal to C, okay, instead of 2C, okay? So W will never exceed the speed of light, okay? So this is also why this formula here, okay, I mean, answering the question that I asked at the very beginning, that this equation is actually having something wrong, right? It doesn't make sense in relativity, right? Because W in principle can become, any speed, even greater than C, okay? So, okay, so this is the result, okay, the addition law of velocities. And now you're asked in the problem set 4 to derive the same result by using 4 velocities. Okay, so you have to think a bit how to make use of 4 velocities, okay, the concept of 4 velocities to derive the same result here. Okay, maybe the notation can be quite different, okay, but the concept would be the same. Okay? I mean, the workflow would be the same. And of course, you may use a different notation like 4 velocities. Okay, so that's all for the first part of this exercise class. So now let's come to the second part, transformation of 4 velocities. Okay, so I would like to emphasize here that the motivation for me to talk about transformation of 4 velocity here is that it seems that many of you are a bit confused about two concepts, which actually was also discussed in our course website's discussion boards. Okay, so actually I replied the questions about the geometrical image of manifolds, and there actually I mentioned that there are two different concepts, right? The first concept is the coordinates of points. Okay, whether points in the space-time, or even more generally speaking, in a manifold. But the reason why we use coordinate system, I mean to impose a coordinate system, is because we want to so-called name the points, right, or the manifold, right? Just like the Earth, right? If we don't have the longitude and latitude numbers, then it's actually quite difficult for us to accurately, without ambiguity, to name any point on Earth, right? But once we have the longitude and latitude on Earth, then we can easily make use of this coordinate system to unambiguously tell which point is which. Okay, so this is about coordinate system, right? And of course, the coordinate system is something that we artificially add, right, to the manifold, right? Because the Earth is the Earth, right? It doesn't really have any coordinate systems, right? So it's something that we human adds on it artificially to make our life easier. Okay, so because it's artificial, then of course it should not be limited to just one coordinate system, right? There should be many different coordinate systems, and that's why we have the need to talk about transformation, right? Transformation between different coordinate systems. Okay, because even if we use different coordinate systems, when we talk about the same points, right, there should be some transformation law between the two coordinate systems, right? So that when I use my coordinate system to name one point, but you want to use your coordinate system, there should be some kind of translation rule or transformation rule for me to tell you that, okay, which point I'm really talking about in your reference frame, right, or in your coordinate systems, okay. So now I have talked a bit about coordinate systems, but actually I have not talked about geometrical objects yet, right? Geometric objects like vectors or even tensors, right? I haven't talked about these concepts, right? But actually, these kind of concepts also depends on the coordinate systems, right? If you want to really quantify these kind of geometrical objects, then coordinate system is also useful for us to represent these kind of objects. But the thing is, the transformation law of the coordinate systems may not be directly applied to the transformation law of this kind of geometrical objects. Okay, so one example would be, I think it's question C1, okay, in problem set 2. Okay, if you recall this problem set, we have two coordinate systems, right? Namely the good old Cartesian xy and also the polar coordinate system r theta, right? So they are coordinates of points, right? And there is no vectors defined yet in the manifold, right? And you should also be very familiar about their transformation law, right? Is the nonlinear equations relating xy and r theta, and one of them is something like an arctangent y over x. So they're very nonlinear, right? So this is the transformation law of coordinates of points, okay, whether in space-time or in more general scenario in the manifold. But when we come to vectors or any other geometrical objects like tensor, okay, the transformation law is actually, in some sense, becomes simpler, right? It involves terms like around x. It also become quite simple, okay? So it just involves the derivative of one coordinate system with respect to another coordinate systems, right? So because the coordinates of points and geometrical objects like vectors are different concepts, so the transformation laws of these two things should also be different, okay? So this is the point that I would like to touch a point here, because we have an observation that many of you really get confused about these two concepts, okay? But now, actually, in contrast to what I have just mentioned just now, what I want to really show here in this part, okay, is that special relativity, okay, or in other words, Lorentz transformation has a very nice property, okay, and the nice property is that the transformation law of coordinates of points and geometrical objects like vectors, or mainly vectors, okay, because we talk about vectors now, actually transform in the same way, okay, namely Lorentz transformation, okay. So why is that, okay? Why is that I just mentioned there are two different concepts, so they should transform differently, but in special relativity, they have the nice property that they transform in the same way, okay? So this is what I want to show in this part. Okay, so to show that, I have designed 3 questions here. Okay, so let's get started. Let's take a look at one by one. So the first question is very straightforward. I just asked you to simply write down the matrix of Lorentz transformation from an inertial frame to a moving frame that moves in the positive x direction of the inertial frame, okay, with speed v, okay, and the v here is constant, okay, it's a constant speed, okay. Again, this is actually very standard, okay. Is really a standard scenario or setting in most of the special relativity textbook or course, okay. Namely, no y direction, no z direction, and even in the x direction, the frame that we talk about move in the positive direction. Right? So if you're very familiar, you might even be able to recite that matrix, something like this. Okay, right. So this is the very standard Lorentz transformation matrix, right? Because no y and z direction is involved. So the y component and z component here are 1. And the time component and x component have the term gamma and beta here, which are defined here, okay, which is also a very standard notation or standard definition in special relativity. And also note that that's here the primed index. Okay, so now you should have noticed that I have used 2 different kind of indices here. The first index here is primed, and the second here is unprimed. Right? So the primed index represents the moving frame, which means that after applying this matrix, what we get would be the vector in the moving frame. Okay, and the vector that we add this matrix on would be the vector that we measure in the unprimed index or the inertial frame. Okay, so make sure that you won't get confused about the indices here. Okay, so which is primed, which is unprimed, which is the inertial frame, and which is moving frame. Okay, really convince yourself that you have a very clear picture about this. Okay, so now let's go to the second questions. Okay, so this is exactly the point I want to make. Okay, by using the Lorentz transformation in part A here, convince yourself that Lorentz transformation can also be applied to components of a 4 velocity. Okay, when we transform the coordinate system in special relativity. Okay, so again, I would like to make this very clear. So normally when we talk about Lorentz transformation, we actually mean something like this, right? Okay, so this is a Lorentz transformation matrix. Okay, we have in part A, and the vector on the right-hand side here is actually the coordinates of space-time points, right, in one frame. And the vector on the left-hand side here is the coordinates of space-time as well, but in another frame. Okay, so the main point here is that they are all coordinates, right? They are not even, in some sense, we won't even call this a vector, right? Because they are just points, okay? They are just a set of number that is assigned to a point, right? So they are just the coordinates, okay? So now we apply this Lorentz transformation to coordinates to get another set of coordinates in another frame, okay? And this is actually equivalent to writing these 4 equations here, right? That means that if we want to get the time components of the first vectors, okay, or the time components of the coordinates of a space-time point observed in the moving frame, okay, what we need to do is to make use of the time component as well as the x component of the inertial frame, right, to get to these components or the coordinates, right, the time components of the coordinates. The same as the x components, okay, it involves or includes the time components and x components as well, right? And because we don't consider y y direction and the z direction. Y and z here are trivial. So the main thing here is these first two equations here. Okay. So how can we convince that this is exactly the same Lorentz transformation when we also want to transform a four velocity? Right? So this is not a four velocity, but now we want to transform a four velocity. So what can we do? Actually, there are two ways to think about this. Okay. So the first way to do this is really to recall or to remind ourselves the definition of a four velocity. So what is four velocity? What is the relationship between four velocity and the space-time coordinates here? Okay. Well, if you are very familiar and if you pay attention in the lectures, you should be able to quickly tell that four velocity is nothing but the derivative of the curve, okay, which is given by the coordinates of the space-time points, okay, with respect to tau, okay, and tau here is the proper time of the particle, okay. So if you get confused here, let me make it slower. Okay? So when we talk about four velocity, of course, there should be something that moves, right? Something that moves in the space-time, right? So if it's moved in the space-time, then there should be a curve in the space-time, right? And if there's a curve in the space-time, then of course there should be some point on the curve, right? Well, actually, curve is nothing but just a collection of many points, right? So so curve, that the curve here is nothing but just the collection of many points, and the points are all represented by the coordinates here, okay, namely t, x, y, and z here, okay, and the four velocity is just the derivative of these coordinates, okay, with respect to the proper time, okay, which is the time that is measured by the moving particle itself, okay? Which means it's the time measured in the inertial frame of the particle itself, okay? If you are still confused about this kind of concept, you may really want to go back to the lectures or even go back to some reference books, okay, on this. But I hope that you get this very clear and what four velocity is really about here. Okay, okay. So as I mentioned, four velocity is nothing but just the derivative of the space-time point here with respect to tau, right? So the most naive way to get four velocity from this expression here is just differentiate both sides of this equation with respect to tau, right? So when we differentiate with respect to tau, the left-hand side, what we'd get would be something like this. And when we differentiate the right-hand side with respect to tau, we should be able to get something like this, right? So now the vectors that we have here is nothing but just the four velocity that we have in the moving frame. And here, this vector here is nothing but just the four velocity that is observed in the inertial frame. Okay, but now the interesting thing is that the Lorentz transformation matrix remains unchanged, right? It's exactly the same as the matrix here, right? So this already proves that the transformation from four velocity in one frame to four velocity in another frame is nothing but just the good old Lorentz transformation here, right? And the reason is, of course, gamma and beta are all constants, right? Right, because gamma and beta is nothing but just quantities that depends on v, okay, the speed with which the moving frames move relative to the inertial frame, and the speed is said to be constant, right? Because we are not considering any acceleration, so the speed doesn't change. So they are all constant. So that's why they remains unchanged when we differentiate both sides. Okay, so we immediately prove that even for 4 velocity, okay, or I should say even for 4 vectors, okay, for vectors, okay, for geometrical objects like 4 velocities like this, they also transform exactly the same way as the coordinates of points, namely the Lorentz transformation. Okay, so this is one way to prove that. But here I would like to give another way to really convince you that this is the case. Okay, this is the very nice property of special relativity. Okay, and that is we really go back to the transformation law for the components of vectors. Okay, if you really are familiar with the transformation law of components of vectors, you should be able to recall that for contravariant vectors, okay, the transformation law looks something like this. Okay, something that involves the partial derivatives, okay, of one coordinate with respect to another coordinate, right? And by saying another coordinates here, I mean the coordinates are in another frame. Okay, so this is exactly the transformation law for vectors. Okay, so this equation should be exactly the same as this equation here, right? So the v mu prime here is supposed to mean exactly the vector here, the components of the 4 velocity here. Okay, the v nu here also is supposed to mean the components of 4 velocity here, right? So this thing here should be exactly these things, right? In order for my claim to be true, right? So is it really the case? This should be something really straightforward to show, right? Because if we differentiate x mu primed, which is nothing but these guys here, okay? If we differentiate, say, one of these x prime here with respect to, say, t, okay, the unprimed t, then what will we get? We can actually just go back to this transformation law of the coordinates of points, and then we just differentiate x prime here with respect to t, right? Or in more accurately speaking, we should differentiate with respect to ct, right? Because ct is a whole coordinates or the time component of coordinates here. Okay, so the result would be nothing but minus beta gamma here, right? Right. You may want to try to differentiate each of the equation here, okay, with respect to each of ct, x, y, and z, okay, unprimed, okay, to see whether you can really get this matrix here. If you get the same matrix, then it means that even if you use the very standard transformation law for components of vectors here, we get the same result, right? Namely, vectors also transforms under Lorentz transformation like this. Okay, and actually that is really something that's trivial, right? Because Lorentz transformation mathematically is a linear transformation, okay? Because it's a linear transformation, it has a nice property that this expression here would reduce to the very same Lorentz transformation here, okay? Okay, so feel free to take some time to think this through, to convince yourself that this makes sense. And it's really nice for special relativity to have this property so that we can almost blindly to use Lorentz transformation to transform almost anything, okay, from coordinate points, okay, space-time points, to geometrical objects like vectors here. Okay. Okay, so let's get to the last part, the last question here, which is just some calculation. Okay, compute the 4 velocity components in the inertial frame of a particle moving in the positive x direction of the inertial frame with speed v. Okay, now you may want to get to pause a little bit to really think about this question. Okay, if you remember, I mentioned that it's very important for you to really be very clear about we are transforming from which coordinate system to which coordinate system, right? So here, the question is asking about the component in the inertial frame of the particle. Okay, moving in the positive direction of the inertial frame with speed v. Here, I really means that the inertial frame of a particle really means the frame that moves with the particle. Or you may just take this as the particle itself, right? But now we have this particle moving in the positive direction, x direction of the real inertial frame, okay, really the stationary frame with speed v, okay? So what is the 4 velocity components of this particle, okay? So this is actually a little bit tricky, okay? Wait a minute. Excuse me, I think I made a mistake. Sorry for the confusion. Sorry for the confusion. Okay, the inertial frame here. Okay, the inertial frame here is actually is really the stationary frame. Okay. Okay. So now we have a stationary frame. Okay, an inertial frame, and now the particle is moving in the positive x direction of this frame. Okay, with speed v. Okay, so from the inertial frame's perspective, okay, which means from the stationary observer's perspective, what would be the 4 velocity of this particle? Right. Yes. So this is the right interpretation of this question. Okay. Sorry for the confusion. So if you think for more while for this, you should be able to find that this is actually just the reverse of what we have done before. Right? So before, we are looking for the quantities in the moving frames, okay, from the inertial frame. Okay, we want to transform the quantities in the inertial frame to the quantities of the moving frame. But now, this is the other way around. We want to transform the quantities of the moving frames to the stationary frames, okay? So things is a little bit reverse. It's just the reverse, okay? So, so this is it, okay? So we have to first, again, Lorentz transformation is the key, right? So as long as you're doing special relativity, Lorentz transformation is the key. So the first thing we want to do would be to write down the Lorentz transformation, the matrix here, that we have to be very careful. We are talking about which frame to which frame, okay? If we are talking about transforming from the moving frame to the inertial frame, we are actually doing like transforming from an inertial frame to a moving frame, but the moving frame is moving in the negative x direction, okay? Right, moving from, it is moving to the negative x direction, okay? So in this way, the beta here would have no negative sign anymore, right? If we are considering the very standard, moving in the positive x direction scenario, if we have the minus sign here. But now we are looking at the reverse. Okay, the moving frame is actually moving in a negative direction. Okay, so we don't have the negative sign. So this would be the Lorentz transformation matrix that we use. Okay, and then we can then use this transformation matrix to transform the force velocity observed by the inertial frame of the particle. Okay, but what is the force velocity of the particle? Okay, if the particle observed itself, what would be the force velocity? Okay, you may want to take a pause to think this through. But if you have the right concept, you should be able to see that the vector is nothing but the one here, okay, C000, right? Because the particle sees itself as stationary, okay, so it won't have any X or Y or Z components or speeds, right? It just stay there, right? It doesn't move. The only curve that it has in space-time in its own frame of reference would be a vertical line, right? Moving along the time axis, right? And that would be C here, okay? So you can also say that the particle move with speed of light in the time direction. Okay, so this is the way to think about this, right? So this is the vectors, the force velocity vectors observed by the particle itself. Okay, and then we transform this force velocity by use of this Lorentz transformation matrix. Then we should be able to get the result for the force velocity in the moving frames. Okay, in this case, the moving frames move in the negative x direction. Or if you look at another perspective, if you come back to this moving frame, which means that it becomes stationary, it becomes inertial frame of u, okay, then that would be the inertial frame. Okay? But we are now transforming the force velocity in the positive moving frame of the particle to your inertial frame. Okay, so I hope that this doesn't get you very confused. Okay, because there are two perspectives of seeing this. Okay, it really depends on whether you look at the scenario from which frame. Okay, from the frame of a particle or from another frame that move relative to the particle. Okay. So this would be the force velocity observed by the other frame, okay, the frame other than the frame of the particle. Okay, so that's pretty much what I want to share in this exercise class. I hope that this has cleared some confusion for you guys, and also I can provide some hints for you to complete problem set 4. So yeah, so I hope it's helpful. Yeah, so well, enjoy your problem set 4. I wish you very good luck.